عليكم طلاب الأحبة، هذا هو الفيديو الثاني من شرح دروس الوحدة الثالثة. نصل معكم إلى galvanic cells. So what is galvanic cells? If we speak about galvanic cells, these are the cells which produce electricity. In galvanic cells we have two separated containers. We have the container of the anode and container which contains the cathode. And the anode, the sign of the anode in galvanic cell is negative. This is the first thing you should know. The sign of the anode in galvanic cell is negative and the cathode is positive. So anode is negative and the cathode is positive. In the galvanic cells here, in this galvanic cell, we are going to use zinc and carbon. As we can see, we use different electrodes. So in galvanic cells, we use different electrons. In this we use zinc, and the other cathode we use copper. And why the anode is zinc and why is copper the cathode? We should use different electrodes which have different potential, reduction potential. The reduction potential of the anode has to be less than the reduction potential of the cathode. The reduction potential of the cathode has to be more. In this case, if you look at the reduction potential of zinc, it is negative 0.76. But the reduction potential of copper is positive 0.34. So as we can see, the reduction potential of zinc is less than the reduction potential of copper. That is why anode is going to be zinc and the cathode is going to be copper. In this cell, we find that solutions of the anode and the cathode are in separated containers. They are not in the same container, because if the solutions and the electrodes of the same solution are in contact, they will produce heat. But if they are separated, they will produce electricity, like this galvanic cell, which is used to produce electricity. We need to have one electrode which has less reduction potential and another which has more reduction potential. So the electrons will flow from the substance with less reduction potential to the substance with more reduction potential. Here in this cell we have the zinc as anode and copper as cathode. Between them there is a wire which connects them. Now what is the function of this wire? To connect between the anode and the cathode, in which the electrons will flow. We can determine the anode and cathode from the movement of electrons. For example, in the ministry exam, they can give you two substances and you don't know which one is the anode, which one is the cathode in a galvanic cell. If they give you the sign like this one, the flow of electron flow from left to right, it means this is the anode and this is the cathode. If they flip the sign, if they give you in the exam the sign of the electron, the arrow points like this, then this is going to be the anode and this is going to be the cathode. How do you know? From the sign of the electron. Now here when we speak about they produce electricity, how they produce electricity? Galvanic cells produce electricity. How? Electrons will flow from zinc to copper half cell. This movement of electrons is the electricity. So what is electricity? Is flow of electrons. What causes flow of electrons? Is we have two electrodes with different reduction potential, and when the electrons flow from the anode to the cathode, this will cause the production of electricity. And that is why galvanic cells produce electricity, because they have different electrodes with different potential, and the electrons flow from the anode to the cathode, which cause the generation of electricity in this case. So if we look at the anode half cell, we call it the anode half cell. The anode half cell contains solution of zinc sulfate. So here we have zinc sulfate and we have an electrode made of zinc. Zinc is immersed in the solution of zinc sulfate, partially, not completely. And in the other cathode half cell, we have solution of copper sulfate, and the electrode of copper is immersed partially in this solution, and they are separated, these two half cells. Between them there is a salt bridge. This is a salt bridge, and we are going to see the function of the salt bridge later. Now let's see what happens here. The zinc electrode is going to be oxidized. That is why if you look at its mass, it is decreasing. Why? Because zinc is oxidized into zinc positive. What is the difference between zinc in the zero state and zinc in its positive state as ion? Ion, these are ions which dissolve in the solution here. So the zinc, which was zero state, like solid, now it is aqueous ions in the solution. So here, zinc, it is solid before oxidation, then it becomes like in the aqueous solution ions. So as the reaction happens, the zinc electrodes is oxidized, so its mass decrease. The mass of the anode decreases. Decreases because zinc is going to be converted to zinc to positive. Therefore, the concentration of positive ions in this half cell, in the anode half cell, will increase. In this half cell, the positive ions will increase. Why? Because zinc becomes zinc to positive. Now let's see here in the other half cell of the cathode. Of the cathode, we have copper sulfate. We have copper sulfate solution. Now the copper sulfate, the copper, which is 2 positive, is going to gain these 2 electrons. Zinc is going to lose 2 electrons, and the electrons will flow from the anode to the cathode. Copper sulfate is going to get these 2 electrons, then it is going to be converted to the zero state. So copper sulfate, copper, which is 2 positive, is going to become copper zero. Copper zero is this one, the electrode. That is why the mass of the copper increases. Now the mass of copper increases. Where this increase come from? It comes from the solution. Because the copper to sulfate is going to gain 2 electrons, then is converted to copper zero state, which will accumulate in this electrode, and the mass of the cathode increase. So mass of cathode increase. The mass of the cathode increase because the copper sulfate ions become copper and accumulate in this electrode. So in this case, the copper positive is going to become zero, and what is going to be left is the sulfate negative. Therefore, the negative ions in the cathode half cell will increase. Let's sum it up. The positive ions in the anode half cell will increase. The negative ions in the cathode half cell will increase. The mass of the anode will decrease. The mass of the cathode will increase. So the mass of zinc will decrease, the mass of copper will increase. In this case, the mass of the anode will decrease, becomes less. The mass of the cathode will increase, will become more. And the salt bridge here, the salt bridge has a function. What's the function of the salt bridge? First, it closes the circuit between these two half cells. It closes the circuit. The second function of the salt bridge is to balance the ions. In the anode cell, we are going to have lots of positive ions. And in the cathode half cell, we are going to have many negative ions. This reaction can reach equilibrium and stops, but the salt bridge will rebalance or balance the charges. What is it going to do? It's going to take sulfate negative ions and keep them in the salt bridge. Now, when the positive ions increase in the anode, it's going to pass these sulfate into the anode half cell. Now the zinc will be balanced by these negative ions. On the other hand, in this cell, the cathode half cell, the negative ions will increase. It's going to take these negative ions. Also, it can take these positive potassium ions back to the cathode half cell. Now we will have balance of ions. Now let's sum it up again. We have electrical Through the wire we have electrical conduction. In the salt bridge we have electrolytic conduction, or we call it ionic conduction. Like when you touch something, when your hand has water, you get like shock of electricity because water conduct electricity. Is it through wire? No, it is through ions of water. In this case, the salt bridge will ensure conduction of electricity, but what type of conduction is going to be electrolytic conduction? That is why it will close the circuit and will balance the charges. Now if it asks you where electrical conduction, that's in the wire, the electrolytic or ionic conduction is going to be through the salt bridge. Now the questions which can be about this diagram: first of all, the sign of the anode, which is negative, the sign of the cathode, which is the positive. Then the mass of zinc decreases, the mass of copper increases, which is the mass of the anode and the mass of the cathode. The concentration of ions, of positive ion in here will increase the positive ion, the negative ion in the cathode will increase. Then it can ask you about the movement of ions. Negative ions, sulfate, move from the cathode half cell to the salt bridge, then to the anode half cell. Then we have the potassium ions can move to the cathode half cell. What type of conduction of electricity here? We have electrical conduction. Here we have electrolytic or ionic conduction. What reaction happens at the anode is oxidation. Oxidation happens to the anode. Oxidation of what? Oxidation of zinc. Zinc will become zinc 2 positive plus 2 electrons. This is the reaction of oxidation. Now let's speak about the cathode. What happens to the cathode? Reduction. Reduction of what? Reduction of copper? No, it's not reduction of copper. It is reduction of copper ions which are in the solution, not of the electrode itself. So ions of copper 2 positive will be reduced into, they will gain 2 electrons and will be reduced into copper 0. So at the cathode what happens is reduction. Remember an ox red cat. So remember an ox red cat, and oxidation happens at the anode and reduction happens at the cathode. Now let's see here. When zinc reacts or in contact of this one, electricity will be produced and zinc will be oxidized into zinc 2 positive plus 2 electrons. What is the oxidation potential of zinc? Is positive 0.76. Copper is reduced. Copper ions, copper 2 positive is going to gain 2 electrons and become copper 0. What is the reduction potential of copper? Is positive 0.34. Now let's see these equations and how we can write it. About the cell, the reaction at anode was the reaction at anode is going to be the reaction at anode. Zinc is going to be oxidized into zinc 2 positive plus 2 electrons. This is oxidation at anode. The reaction at cathode, what happens? Copper ions, copper 2 positive plus 2 electrons will become copper 0. Reduction at cathode. Let's see the overall reaction. The 2 electrons with 2 electrons. Now the overall reaction should be written by what comes before the arrow from both equations. Then we make the arrow, then we complete it with what comes after the arrow in both equations. So here we have zinc plus copper 2 positive arrow. Then after the arrow we have zinc 2 positive plus copper, which is the 0 state. Now let's see here what happened at At the anode, zinc. Then at the cathode, we have copper ions. After the arrow, after oxidation, zinc to positive. After reduction, copper will be copper 0. The cell diagram notation. To write the cell diagram notation, we write the anode before, then after. And this two lines which represent the salt bridge. Then we write the cathode. Cathode before, then after. Let's apply this one. So before oxidation, the anode was zinc. After oxidation, it will become zinc to positive. Then we have the salt bridge here. If you don't have salt bridge, if you have porous barrier, which is membrane, we are going to write like dotted line, like this one. This means barrier, porous barrier or membrane, which allows the movement of ions but not mixing of the solutions. So in some cells we can use the salt bridge or we can use porous barrier. Now this zinc before, zinc after. Let's complete it. Now let's see copper. Copper before reduction, Cu to positive. Then after, it is this one, copper. This is what we should focus on when we write the cell diagram notation. In this half cell, we need to have oxidation. In this half cell, we need to have reduction. How do you know your work is correct? What comes in the middle has to be greater than what comes before and after. Now zinc 2 positive, this is 0. This is 2 positive, this is 0. So we had oxidation in this side and we had the reduction in this side. So our work is good. Calculating the electromotive force. Now let's calculate the electromotive force. We had in the equation the oxidation potential of zinc, which is positive 0.76 volt. And we have the reduction potential of copper, which is 0.34 volt. To calculate the electromotive force, we have two methods. The first one, we will see electromotive force equal oxidation reduction of anode plus reduction potential of cathode. In this case, we have the oxidation of zinc and we have the reduction potential of copper. So let's see, oxidation electromotive force equal the oxidation potential of zinc, which is positive 0.76, plus the reduction potential of copper, which is 0.34 volt. This equals 1.1 volt. As we can see, the sign of the cell has to be positive, so it is galvanic cell. If the sign is negative, then the reaction is not in a galvanic cell, and we can say it is non-spontaneous. But in this case, it is spontaneous, and it is galvanic cell. So how we calculate the electromotive force? Oxidation of the cathode, oxidation potential, plus reduction potential of the cathode. The first way. The second way, we can use another rule. We say electromotive force equal the reduction potential of cathode minus the reduction potential of anode. This is positive 0.76 is the oxidation potential of zinc. Now let's write the reduction potential. It will be the same but with different sign. the reduction rate of zinc is negative 0.76, the same like the first one, but with negative sign. Now the reduction potential of copper is positive 0.34. As we can see here, this is less value reduction potential, then it is anode, and this copper is the cathode. The rule says electromotive force reduction of cathode minus reduction of anode, which means reduction of copper minus reduction of zinc, which is positive 0.34 minus negative 0.76, which equals 1.1 volt. The same like the one before, but this is how we calculate it in case we have oxidation potential and a reduction potential, or if we have both reduction potential, how we calculate it in both ways. Now let's see here some questions about the cell to see we understood it or not. Let's analyze this diagram. Questions about it could be like these. True, false questions. Number 1 represent the cathode. Now number 1, this is number 1. Number 1, the electron moves from 1 to 3. So this is the anode and this is the cathode. It tells us represent the cathode. Number 1, false. It is the anode. Anode. 2, question 2. Positive ions increase in number 2. Now in number 2 here in this solution, it tells us that the positive ions increase. Yes, true, because the anode will be oxidized. For example, if this is zinc, is going to become zinc to positive. So the positive ions here will increase. This is correct statement. The oxidation potential of 1 is greater than 3. Now the oxidation potential of 1 is greater than 3. True. This is true. But the reduction potential of 1 is less than 3. If we speak about oxidation potential, then the oxidation potential of the anode is greater than the oxidation potential of the cathode. But if we speak about reduction potential, the reduction potential of anode is less than the reduction potential of cathode. But if we speak about oxidation potential, the oxidation potential of the anode is greater than the oxidation potential of the cathode. So we speak about oxidation or reduction. Later we will have more idea about this one. Now then the mass of number 3 will increase. Number 3, the mass of number 3 will increase. Yes, because it is the cathode and the mass of the cathode increase. True. Number 3 will be reduced. Number 3, the electrode itself will be reduced. False. We said the electrode itself will not be, the cathode itself will not be reduced. The ions of the solution here we have ions. For example, if we have copper 2 positive, these ions will be reduced and accumulate on the cathode. So not the cathode itself will be reduced, but the ions in the solution. So this one will be false. The number 4 will be reduced, not number 3. Number 1 will be oxidized. Number 1, yes, number 1 will be oxidized because it is the anode. And the anode itself will be oxidized. Negative ions will move from the salt bridge to number 2. Now, if we look at the negative ions, like sulfate, for example, sulfate here in the cell, sulfate, we said negative ions will move to the salt bridge. Then these negative ions will move to number 2. That is correct, to the anode half cell. Electrical conduction happens through part 5. Part 5, electrical conduction. Is it true? False. It is, we said electrolytic or ionic. So this should be false. The electromotive force of the cell will be positive. For sure, it will be positive because it's galvanic. It says heat will be produced in the cell. No, because they are in separated containers, so electricity, not heat. Now let's see here type of questions. Type of questions about galvanic cells. What type of questions they could ask us? Well, in the exam, we'll have questions about galvanic cells, and these are some of the examples how the questions can be. The first type of question, they give us only the reduction potential of the anode and cathode, and they do not give us anything else. No equation, nothing. For example, let's see this question. It says the reduction potential of magnesium. So it gave us the reduction potential of magnesium and copper. This is magnesium, and this is the reduction potential of copper. So we have the reduction potential of magnesium and we have the reduction potential of copper. As we can see here, the reduction potential of magnesium is less than the reduction potential of copper. Therefore, magnesium is going to be the anode and copper is going to be the cathode. And we know at the anode, oxidation, and the cathode, what happens? Reduction. So we determined what's the anode and what's the cathode from the reduction potential. Now we are going to see what is in the question. The question asks us about what is the reaction at anode. The reaction at anode, it will involve magnesium. And what will happen to magnesium? It will be oxidized into Mg2 positive. So which reaction here involves oxidation of magnesium? We see magnesium from 0 to magnesium to positive. So number 1 is the correct answer, because at the anode, magnesium is going to be anode. So magnesium is going to be oxidized at the anode. So this is the correct answer, number 1. So this one type of question can ask you about what's the reaction at the anode. It can give you the same question, but in this, it will ask you what is the reaction at the cathode. At the cathode here, we agreed that copper is going to be cathode. And what happens at cathode is reduction. So reduction of copper is going to be copper 2 positive plus 2 electrons is going to be copper 0. So in which equation we have the same? This is magnesium, no, because anode, magnesium, anode. Copper oxidation, no, it will not be oxidized, it will be reduced. So the answer is number 4. Let's see here. The reduction potential of magnesium and copper are respectively the same question, but it asks us about the overall reaction. The overall reaction is going to involve oxidation of magnesium and reduction of copper. So Mg plus copper to positive, that's going to be Mg to positive plus copper, which is 0. It is better when you answer questions, you do it before you read the choices. This way you will not be confused with the choices. So now, in which equation we have oxidation of magnesium and reduction of copper? This will be oxidation, then reduction, no. This is, there is no reduction of copper, no. This is oxidation of magnesium, and this is reduction of copper. So this is the correct answer. We're going to choose this answer. Let's see here the fourth question. It can tell you the reduction potential of magnesium and copper respectively these. What is the cell diagram notation? The cell diagram notation is going to involve oxidation of magnesium and reduction of copper. It has to be anode before and after, cathode before. No, this is cathode after. Cathode, no, because copper is cathode. Anode before, anode after, yes. Cathode before, cathode after, yes. In the middle, greater value than in the outer side. So this is the correct answer. This is no, because the oxidation of reduction of magnesium, oxidation of copper, this is wrong arrangement. So this is not galvanic cell. This is the correct answer. Let's see here another idea. The reduction potential of magnesium and copper are respectively negative 2.37 and positive 0.37. 34. What is the electromotive force? The electromotive force here, we have both reduction potential. Both are reduction potential. So we are going to say electromotive force equal reduction of cathode minus reduction of anode. We agreed that copper is the cathode, so we're going to see positive 0.34 minus negative 2.37. You are going to calculate it, and that is going to equal, and the answer is going to be positive 2.71 volt, which is the choice number 4. So these are the type of questions which can be like this one. Let's see here another type of question. We determine the anode and the cathode from the flow of electrons. Here, anode and cathode are determined by the flow of electrons. They don't give you the reduction potential of the substances, or they can give you the reduction potential, but they tell you electrons flow from substance to another. Like this one, electrons flow from zinc to cobalt. Now zinc is going to be anode because electrons flow from the anode to the cathode, and cobalt is going to be cathode. So zinc is going to be oxidized and cobalt is going to be reduced. It tells us what is the reaction at anode. Anode is going to be oxidation of zinc. Cobalt, we agreed it will be cathode, so wrong. The second choice wrong. Now zinc is oxidized. This is the correct answer. It gives you electrons flow from zinc to cobalt. What's the reaction at cathode? Cathode is going to be reduction of cobalt. So here this is not reduction, it is oxidation. This is the reduction of cobalt. Magnesium has nothing to do here, so the correct answer is number 2, because this is the cathode and the cathode will be reduced. Let's see here another question. It tells us the electrons flow from hydrogen to copper. Now let's see, from hydrogen to copper. Now hydrogen is anode. What happens to anode is going to be oxidized. Hydrogen, which is 0, is going to be hydrogen positive, and copper is going to be from copper to positive to copper. Now we're going to find equation which has hydrogen to hydrogen positive, copper to positive, copper. Now copper, it started with copper, started with the cathode. This is wrong. Hydrogen 0, hydrogen positive, correct, but copper is oxidized. Now we have 2 oxidations. No, we don't have equation with 2 oxidation. Hydrogen 0, hydrogen positive, oxidation of hydrogen, true. Copper to positive copper, reduction of copper, true. So this is the correct answer. Let's see here other type of questions. It gives you the reduction potential are given with ionic equations, and now these questions are going to be easy. We can determine from the equation, we have complete equation. We have in this equation cobalt plus lead to positive, cobalt to positive, lead. Now cobalt is oxidized, and lead is reduced. So if it tells you what is the reaction at cathode, Ca is going to be CO to positive plus 2 electrons. Reaction at anode was the reaction at cathode. At cathode, Pb to positive plus 2 electrons is going to be Pb. If it tells you what is the cell diagram notation, CO to positive, Pb to positive, Pb, that is it. And here we have reduction potential of cobalt and lead are these. So as we can see here, what is the anode? The anode is this one because it is less value, the cobalt, and this is more value, more reduction potential. So it's cathode, this is anode, and this is cathode. So the rule to calculate the electromotive force will be reduction of cathode minus reduction red cathode minus a red anode, that's going to be negative 0.13. This is the cathode, minus negative 0.28. Calculated, it will be positive something volt. You can complete it, and these type of questions, which can be about questions like these. Let's see the other type of question. It tells you the reduction potentials are given with neutral equation. Now in this case you need to determine what was positive, what is zero, what was zero and became what is oxidized and what is reduced. If we look at this one here, copper is zero. Copper after the arrow is to positive, so copper from 0 to positive. Ag positive, it becomes 0. So what happened to copper is oxidation. What happened to Eg here is reduction. So the reaction at anode will be copper to positive plus 2 electrons, and the reaction at cathode to Ag positive plus 2 electrons to Ag. The cell diagram notation, copper to positive, then we have to Ag positive to Ag. Then the electromotive force, you calculate it because you have reduction of copper and reduction of silver. You have them here. Which is less? This is less, so this is anode, which is more reduction potential. This is, so it will be cathode minus anode. You'll find the electromotive force. Let's look at another way of having the questions. In such questions, it gives you one equation: zinc to positive plus 2 electrons, copper to positive plus 2 electrons, copper. It gave us here oxidation at anode, and it gave us another equation which is reduction at cathode. We don't need to do anything. We will just, if it asks us about the cell diagram notation, is going to be zinc before zinc. This is the anode, then the cathode, copper to positive, copper. If it tells us about the electromotive force, here we have oxidation and here we have reduction. So we are going to see oxidation of anode plus reduction potential of cathode. The oxidation of anode is positive 0.76 and the reduction of cathode is positive 0.34. That will equal 1.1 volt. If we have one oxidation, one reduction, we just add them together. We do not minus cathode minus anode. Or you should make the oxidation of the anode the reduction, then you use the rule reduction of cathode minus reduction of anode. Let's see here another way of having the questions. In this question, reduction, half cells are given. Now this zinc to positive plus 2 electrons, zinc reduction. This is reduction cathode. Here Sn to positive plus 2 electrons, Sn also reduction. It should be cathode. Now we cannot have like a reaction which happen both at the cathode. One has to be anode, one has to be cathode. So in this case we should flip, we should reverse the equation. One of them should be reversed. Which equation we should reverse? We should reverse the equation with less reduction potential. And which of these two equations have less reduction potential is the equation of zinc, because its reduction potential is negative 0.76. It is less than negative 0.14. And you know, when the negative value increases, the value decreases. So negative 0.76 should be reversed. this equation of zinc should be reversed, therefore it will be oxidation at anode, not reduction. So if we reverse this equation, it's going to be zinc, arrow, zinc, we make the reactant product, and the product we should put them in the side of the reactant to positive plus 2 electrons, and we are going to change the value. Here it is the value of reduction, we're going to make it positive 0.76, because now this one will be what will be oxidation. The second equation will be the same, nothing will change in it. Sn to positive plus 2 electrons will give us Sn, and this is negative 0.14. Now the cell diagram notation is going to be Zn, Zn to positive, to lines Sn to positive Sn. The electromotive force, we're going to add these together. So electromotive force is going to be positive 0.76 plus negative 0.14, and that equals positive 0.62 volt. So it is galvanic, and this is the electromotive force of the cell. If it asks you about the overall reaction, is going to be the overall reaction zinc plus Sn to positive, arrow zinc to positive plus Sn. This is the overall reaction. This is the cell diagram notation. This is the electromotive force. This is the overall reaction. Let's look at another equation here. It says the oxidation potentials are given with half oxidation. Now in this case it will give us two oxidation reactions. Ni, nickel, is going to be oxidized, so this should be anode. Sn is going to be oxidized, this also is anode. So we do not have two reactions at anode. One of them should be reversed. We should make one, we should reverse. The same idea we used before, we reverse the equation with less reduction potential. We are going to reverse the equation with less reduction potential. Which one has less reduction potential? Positive 0.25 or positive 0.14? It is positive 0.14. So the second equation, this equation should be reversed. How we reverse it? Let's see. The first equation is going to be as it is. Ni, oxidation, Ni to positive plus 2 electrons, and this will be positive 0.25. The second equation is going to be reversed. We are going to see Sn to positive plus 2 electrons, the product in the side of the reactant. Then the reactant are going to be in the side of the product. The potential, the reduction potential, we are going to reverse the sign of it because we reverse the equation. It's going to be negative 0.14. Now we can find everything. The equations, we have oxidation and we have reduction. Reaction at anode, Ni, this is the reaction at anode, and this is the reaction at cathode. So Ni to positive, Sn to positive, Sn. This is the cell diagram notation. Overall reaction, Ni plus Sn to positive, it will be Ni to positive plus Sn. Electromotive force, oxidation of anode plus reduction of cathode, because we have one oxidation, one reduction, so it's going to be 0.25 plus negative 0.14, that equals positive 0.11 volt. So the reaction is spontaneous, it is galvanic cell, and everything is clear. Now how we answer questions about this one. Let's see other type of questions. In some questions it will give us the cell diagram notation and can give us the reduction potential of anode and cathode. Then we are going to determine here. Zinc in this equation is anode. What happened to it is oxidation. This Pb to positive lead is going to be reduced. So it will be cathode. It tells us what is the anode. The anode is, this is the anode, zinc. It tells us what is the cathode. The cathode. The cathode, this is the cathode half cell. The cathode should be in free state, in zero state. We should not choose this one. We should choose this one in zero state, because the anode and the cathode should be free elements in their zero state. In this case, the cathode is going to be Pb, not Pb to positive. If it tells you what is the reduced substance, it's going to be this one, not this one. But if it asks you about the cathode itself, you are going to choose Pb, not Pb to positive. The oxidizing agent. The oxidizing agent is the substance which is reduced. This is the substance before the arrow which is reduced. So the substance which is the oxidizing agent is Pb to positive. The reducing agent is going to be zinc. Zinc. The electromotive force, we have reduction of anode and reduction of cathode, both are reduction. So electromotive force reduction, rid of cathode, minus a rid of anode. In this case, the reduction of the cathode is negative 0.13 minus the reduction of anode negative 0.76, that equals positive 0.63 volt. So this is the electromotive force of the cell, and it is a spontaneous reaction. Let's look at the last type of question, which can be, they give us non-spontaneous reactions. They give us non-spontaneous reaction, and we should determine the anode and the cathode from the equation, not from the reduction potentials. In this question, we can make great mistake if we determine the anode and the cathode from the reduction potential. For example, this is less reduction potential, so we are going to see it is anode. This is more reduction potential, so we are going to see copper is the cathode. But if we look at the equation itself, let's see what is in the equation. Magnesium is 2 positive and chlorine is negative. Magnesium is 0, chlorine is 0. Now magnesium, Mg, 2 positive. After the arrow, it is Mg, 0. So what happened to magnesium is a reduction. So magnesium is the cathode, not the anode. If we look at chlorine, chlorine is negative and became 0. Chlorine, negative, it will be oxidized into chlorine. So this is oxidation, oxidation. So this is the anode. Now this is not magnesium, here is the cathode, and chlorine here is the anode. If we find the electromotive force is a reduction of cathode, reduction potential of cathode minus reduction potential of anode. In this case, the reduction potential of magnesium, which is the cathode, we are going to see negative 2.37 minus the reduction potential of anode, which is positive 1.36, that equals negative 3.73 volt. Now let's see here, from this value we will determine that the reaction is non-spontaneous. It is non-spontaneous. It consumes electricity. It did not produce electricity. It is an electrolytic cell, not galvanic. So we concluded all these ideas from the reduction potential because negative value, and the negative value is not in a galvanic cell. It is a non-spontaneous reaction. So what we need to care about this, if you have equation in front of you, you should determine the anode and the cathode from the equation, not from the reduction potential, especially if the reaction is non-spontaneous, because it will not tell you this is a non-spontaneous reaction. It will just give you equation and you calculate. Now here let's see about the hydrogen electrode. The hydrogen electrode, it is used to determine the reduction potential of the other substances. Scientists agree to use hydrogen because hydrogen has fixed value because it is the reduction potential of hydrogen is 0. Now, in the hydrogen electrode half cell or standard hydrogen electrode, if hydrogen is connected to a substance with positive value, hydrogen has less reduction potential, so hydrogen is going to be the anode, and the substance with positive value is going to be the cathode. The substance is easier to be reduced. Hydrogen is easier to be oxidized. Now let's see here. If hydrogen is connected to a substance with negative value, the substance with negative value is going to be the anode, and hydrogen is going to be the cathode. The substance is easier to be oxidized. Hydrogen is easier to be reduced. Now, because the value of hydrogen is 0, if we connect hydrogen with a substance with positive value, the electromotive force of the cell will be the reduction potential of the substance with positive value. If we connect hydrogen with another substance which has negative value, the electromotive force will be the oxidation potential of the substance, the oxidation potential. Now here, if we connect hydrogen with a substance which is positive, electrons will flow from hydrogen to the substance which has positive value, because hydrogen will be the anode and it will be oxidized. If we connect hydrogen with a substance with negative value, the electrons will flow from hydrogen to the substance which has negative value, because the substance will be anode. If we connect hydrogen with a substance which has negative value, the electrons will flow from the substance with negative value to hydrogen, which means the substance will be the anode and hydrogen will be the cathode. Let's look at one example here. It says copper is connected to hydrogen, half cell. Copper is connected to hydrogen. Copper, the reduction of copper and hydrogen are positive 0.34 and hydrogen 0. The reduction potential of hydrogen is 0, which means this will be cathode and hydrogen will be anode. Reaction at anode will be the oxidation of hydrogen. So hydrogen H2 positive will be oxidized into 2 H positive plus 2 electrons. This is oxidation of hydrogen. The reaction at cathode is reduction. Reduction of what? Reduction of copper. So copper to positive plus 2 electrons will be copper. Overall reaction, sometimes they ask us about, they tell you electron move from hydrogen to substance to copper. What's the overall reaction? The overall reaction is going to be, in this case, H2 plus copper to positive is going to be 2H positive plus copper. Cell diagram notation. The diagram notation is going to be anode before, anode after, cathode before, cathode after. The electromotive force is going to be positive 0.34. Why? Because let's see here, reduction of cathode, which is electromotive force equal reduction of cathode, which is positive 0.34 minus reduction of anode 0 equal positive 0.34 volt. The electromotive force of the cell is the reduction potential of copper. Let's look at another question here. It says zinc is connected to hydrogen. Zinc is negative 0.76 and hydrogen is 0. So zinc in this case is the anode and hydrogen is the cathode. So reaction at anode, zinc will be oxidized zinc to positive plus 2 electrons. Reaction at cathode, hydrogen is going to be reduced to H positive hydrogen plus 2 electrons is going to become H2. Overall reaction is going to be zinc 2 electrons with 2 electrons, and put the two equations together. Zinc plus 2H positive will give us zinc to positive plus H2. Diagram notation, zinc to positive. We have here to hydrogen positive, hydrogen 0. The electromotive force will say 0 minus the reduction potential of cathode minus negative 0.67. That's going to be positive 0.76 volt, which is the oxidation potential of the anode, which is zinc in this case. Here, we need to have a look at the electrochemical series. I just put here some of the values of the reduction potential, oxidation potential of some substances to know how we understand this series when we read it or determine the value. If we look up here, we have lithium. Lithium is going to be, the reduction potential of lithium is negative 3.04. And if we look down at the bottom here, we have fluorine. The reduction potential of fluorine is positive 2.87. Now let's see here. When the reduction potential decreases as we go up, it decreases the reduction potential, it becomes more negative. So the value becomes less. When the reduction potential decreases, the strength of the reducing agent will increase. Now here we have strong. As we go up, we have a strong reducing agent. When the reduction potential is negative, is going to be anode. The substance is going to be anode. It is going to be oxidized. Is going to be reducing agent. Now, the more negative value or the less reduction potential, the stronger the reducing agent. Let's go down here. As the reduction potential increase, as the oxidizing agent increase, when we go down, the substance will be cathode. It will be reduced. It will be oxidizing agent. So the more the value of the reduction potential, the more the strength of oxidizing agent. Now, if we speak about oxidizing and reducing agent, what is the strongest reducing agent? The strongest reducing agent is going to be the least value of reduction potential, which is lithium. So lithium is the strongest reducing agent. If we speak about oxidizing agent, which substance has the more value is the strongest oxidizing agent. Now, fluorine is the strongest oxidizing agent. Let's say again. If we speak about the strongest reducing agent, that is going to be lithium, because it has the least value of reduction potential. If we speak about the strongest oxidizing agent, that is going to be fluorine, because it has the highest reduction potential. If we speak about the weakest oxidizing agent, that is going to be lithium ion, because it will be the opposite. It will be here, it will be the weakest oxidizing agent. If we speak about the weakest reducing agent, that is going to be the ion of fluorine. So fluorine is the strongest oxidizing agent. Fluorine ion is going to be the weakest reducing agent. The strongest oxidizing agent is the weakest reducing agent. Just memorize it like this. The strongest oxidizing agent is the weakest reducing agent. The strongest reducing agent is the weakest oxidizing agent. Now let's see here another idea which is very important. The reduction potential of lithium is positive. And the reduction potential of the strongest reducing agent is negative. The oxidation potential is the same like the reduction potential, but with opposite value. So the reduction potential of lithium is negative 3.04, but the oxidation potential of lithium is positive 3.04. Now here, if we look down, the reduction potential of fluorine is positive 2.87, but the oxidation potential of fluorine is negative 2.87. Let's have some questions which can be confusing a little bit. What is the reduction potential? The reduction potential of strongest reducing agent, that is going to be negative 3.04 volt. The same question, what is the oxidation potential of the strongest reducing agent? That's going to be positive 3.04 volt. What is the reduction? What is the reduction potential of the strongest oxidizing agent? That's going to be the highest value, positive 2.87. If the question tells you what is the oxidation potential of the strongest oxidizing agent, that's going to be negative 2.87. You should memorize that lithium is the strongest reducing agent and fluorine is the strongest oxidizing agent. Or in ministry question, they tell you what is the best oxidizing agent, you will see fluorine. Now here, let's see. Element have potential. What is the strongest oxidizing agent? Let's see here. Questions like these. Element A, B, C, D. This is A, this is B, this is C, this is D. What is the strongest oxidizing agent? Strongest oxidizing agent, highest value. Now, the highest value from them all, from all of these, what is the highest value? Is this one, negative 0.2, is more than all the values. So number one, element A is the strongest oxidizing agent. It tells you here, element A, B, C, D have oxidation potentials. What is the strongest oxidizing agent? Now A, B, C, D. In this case, we are going to, it tells us the oxidation. These are oxidation potentials. The oxidation potentials, as you can see here, the oxidation potential of the strongest is the least value. So we are going to choose from here this element, the least value. The least value is in this element, D. So the strongest oxidizing agent has the oxidation potential, this negative 1.2, which is the least value. Now let's look at these questions. If tells you have reduction potential, we are going to choose the highest value. If the question asks us about the oxidation potential, we are going to choose the least value. Now let's see here. If we speak the strongest, the same if it tells us about the strongest reducing agent. Strongest reducing agent, we should choose less value. But if it asks us about the oxidation potential of the strongest reducing agent, we are going to choose the highest value. Let's see this question here. Sometimes it can give us questions like these. The strongest oxidizing agent, highest value of reduction potential. So we are going to see which one has the highest reduction potential here. Let's see. Sn to positive Sn. What happens here is reduction. Here, reduction. And negative. It is negative. Is it the highest value? No. Let's see. Br, negative, Br. This is not reduction. This is oxidation. So we should make it reduction. The reduction of this one will be Br to Br negative is going to be positive 1.07. Let's see. Hg to positive Hg. This is also reduction. We should make it oxidation. To make it oxidation is going to be negative 0.788. This one from 0 to positive oxidation. Yeah, this is oxidation potential. Now all of these potentials are oxidation. What is the highest value? What is the highest reduction potential here? Now we have, this is a reduction potential. This is reduction potential. This is a reduction potential. We flip the sign. This is reduction potential. Which of them has the highest value? Is this one, number 2, because it is positive 1.07. So this is the correct answer. Let's see here. Then we have ideas about reactivity and displacement. When we speak about reactivity, we can determine the reactivity of the elements from their reduction potential. Now, if we have metals, the metal with less reduction potential is more reactive than the metal with more reduction potential. If we speak about nonmetals, the nonmetal with more reduction potential is more reactive than the nonmetal with less reduction potential. Now, if we look at here, the metals A, B, C, D. What is the most reactive? Now it is asking about the most reactive element. We said metal, the less reduction potential, the more reactive. So which one has less reduction potential? Is this one, number D. So what is the most reactive element here? It will be element number D. Let's see here. The metals A, B, C, D have reduction potential the same A, B, C, D. What is the least reactive? The least reactive, we will choose the more value, the more reduction potential. Which one has the more reduction potential? This one is the highest value of reduction potential. So this is the least reactive. This is the most reactive, the highest negative. The least negative is the least reactive. Let's see here. Nonmetals. Now nonmetals A, B, C, D have reduction potential positive. This is A, this is B, this is C, this is D. What is the least reactive? The least reactive. Now Non-metal, more reduction potential, more reactive, is directly proportional, not like non-metals, not like the metals. So the non-metal which have reduction potential, what is the least? The least which has the less reduction potential, which is also number D, is the least reactive. What is the most reactive? The most reactive, the one which has the highest value. This is 0.5 is the most reactive non-metal, but this is the least reactive non-metal. So this is ideas about this one. Now let's speak about displacement. Displacement, if we have metal which is more reactive, it will displace a metal which is less reactive. For example, if we have zinc plus copper sulfate, the reduction potential of zinc is negative 0.76. The reduction potential of copper is positive 0.34. Now, as we can see, zinc has less reduction potential, so it is more reactive. Copper has more reduction potential, so it is less reactive. So zinc can displace copper and kick it out from the compound. We will have zinc sulfate plus copper. Copper now is alone. Zinc took its place. But if we look at this example here, if we look at copper plus zinc sulfate, now copper positive 0.34, zinc negative 0.76. Which one is more reactive? Zinc is more reactive. Can copper kick it out and displace it? No, it cannot displace it. This reaction will not happen. No displacement in this case because copper is less reactive than zinc. So copper cannot kick out zinc from its solution. Now let's see here. Questions. It tells us which will make copper sulfate lose its blue color. Copper 0, no color. Copper to positive is blue. Now this question tells you which of the following is more reactive than copper. Copper sulfate is blue and the reduction potential of copper is positive 0.34. Now which of these elements is more reactive than copper so it can kick it out from its solution, which makes it lose the blue color? Let's see. The first one, Ag. If we say Ag plus copper, Ag is positive 0.80. It is less reactive than this one because more reduction potential. So this one cannot kick it. No reaction. If we look at J, mercury is positive 0. Also more reduction potential, so is not more reactive. But zinc, yes. Zinc is negative 0.76, so it can kick copper out. If copper is removed from its solution, it will lose its color. So which of the following will make copper sulfate lose its blue color is going to be zinc. Let's see the question in a different way. If we place copper in one of the following solution, the solution will turn blue. Now it means what? One of the solutions, if we put copper, which is positive 0.34, we should put it in one of the following which is less reactive. Now, which one is less reactive than copper? Copper is positive 0.3. Zinc is negative. No, zinc is more reactive. Magnesium is way more reactive. Ag positive 0. Yes, it is less reactive. So copper can displace it and the solution can be blue. Now, if we have copper plus Ag, Ag here in O3, copper, this is positive 0.80. So this is less reactive. Copper can kick it out and the solution will be copper NO3 plus Ag. This is blue solution. Which of the following, if we place copper in one of the following solutions, the solution will turn blue. This question tells you Copper is more reactive than which one? Is it more reactive than magnesium? No. Is it more reactive than Ag? Yes. Is it more reactive than zinc? No. Is it more reactive than aluminium? No, because all of them have negative values except this one, Ag, which has more reduction potential, which is less reactive. So copper can make blue solution if we place it here in AgNO3. The last point here, the last idea, we are going to speak about keeping a solution in a container. If we keep a solution in a container, this container should be less reactive than the solution. The ion, the solution, for example, this one, look here. If we have copper sulfate, and here we have, let's say, copper sulfate as well, copper sulfate. The reduction potential of copper is positive 0.34, and this is positive 0.34. This container, if it is made of metal, and this metal, let's say, the reduction potential of the metal negative 0.5, and this metal, the reduction potential of this metal is positive 0.5. Now, can we keep this copper sulfate in this solution, in this container? Can we keep the solution of copper sulfate in this container? How we judge, how we say yes or no, we can or we cannot. We determine this by the reactivity of the metal of the container. This metal negative, the reduction potential of it is negative 0.5. So it is more reactive than copper. It will displace copper and kick it from the solution. So the container will dissolve to the solution, and the solution will change from copper sulfate to the ion of the solution. So in this case, we cannot keep copper sulfate in this container. But let's see this one. The reduction potential of this container is positive 0.5, so it is less reactive than copper. This is less reactive than copper, so we can keep the solution in this container because this container will not dissolve in the solution. It will not displace copper, so we can keep this solution in this container. Let's see here. This question says, if we see in which of the following containers we can keep solution of copper sulfate, the reduction potential of copper is this one. This is negative 2.13 and this is positive 0.80. This is more reactive. We cannot keep copper in this solution in this container, but we can keep the solution of copper in this container because it is less reactive. It will not displace copper. If we look at this question, if we have metal A, B, C, D, this is A, this is B, this is C, this is D, this is E. It says this is E and this is F, the last one, F, respectively. Ion of B positive cannot be kept in containers made of. Now, ions of B, which is negative 0.5, cannot be kept in containers made of metals which are more reactive. Which containers are more reactive? The containers which have less reduction potential. So anything less than negative 0.5, we cannot. The first one, it is negative 1, so it is more reactive. We cannot keep it in container A. Container C, we can. Container D, we cannot because more reactive, less reduction potential. Container E, we cannot because it is also less reduction potential, so it is more reactive. Container negative 0.2, it is more, so it is less reactive. So which of the following cannot be kept in which containers? We cannot keep it in A, in D, and A. In A, in D, and E. So this is the correct answer. We cannot keep this solution of ions of B in these containers in A, in D, and E. And that is it. I hope you got benefit from this fast revision in this video. And we will have another video for the last part of chapter 3. Until then, ciao.